Okay, in last lecture we have studied object modeling. Let us turn towards dynamic modeling. The resulting set of state diagrams constitutes dynamic model. In summary, the following steps are performed in constructing a dynamic model. Prepare a scenario of typical interaction sequence. Identify events between objects. Prepare an event trace for each scenario. Build a state diagram. Match events between objects to verify consistency. While doing your project, you should, whenever you have done a problem statement, after the problem statement, you should prepare a scenario regarding interaction sequence. Then identify the events between the two objects, between two modules. Then a tra- prepare a event trace for each scenario. Then build a state diagram regarding this problem statement. Match the events between objects to verify the consistency. We will see each and every point in detail. So first, preparing a scenario. Prepare one or more typical dialogues between user and system to get a feel for expected system behavior. These scenarios shows major interactions, external display formats, and information exchanges. Approach the dynamic model by scenarios rather than trying to write down the general model directly. To ensure that important steps are not overlooked and that the overall flow of the interaction is smooth and correct. While doing a scenario, you should know the communication between user and system to get a feel for expected system behavior. The scenario shows the major interactions, external display formats, and information exchanges between the two modules. The dynamic model scenarios rather than trying to write down the general model directly to ensure that the important steps are not overlooked and that the overall flow of the interaction is smooth and correct. So sometimes the problem statement describes full interaction sequence, but most of the time you will have to event at least at least flesh out the interaction format. Sometimes problem statement have more accuracy than expected, but sometimes there is a vague or in problem statement or ambiguity in problem statement, so you should have to flesh out that interaction format. For example, in case of ATM, problem statement indicates need to obtain transaction data from user, but is vague about exactly what parameters are needed and what order to ask for them. Suppose I want to withdraw money of rupees 2000, then sometimes machine will dispenses 2000 rupees note, or sometimes machine dispenses three 500 rupees notes and five 100 rupees notes. So there is a value about exactly what parameters are needed and what order to ask for them. So problem statement may specify needed information but leaves open the manner in which it is obtained. So in many applications, gathering input is made major task or sometimes the only major task. The dynamic model is crucial in such applications. First, prepare scenarios for normal cases, interaction without any unusual inputs or errors. Then consider special cases such as omitted input sequences, maximum and minimum values, and repeated values. Then consider user error cases including invalid values and failure to respond. So for many interactive applications, error handling is the most difficult part of the implementation. If possible, allow the user to abort an operation or a rollback to well-defined starting point at each step. Finally, consider various other kinds of interactions that can be overlaid on basic interactions, such as help requests and status queries. So, a scenario, first we will see what is the definition of scenario. A scenario is a sequence of events. An event occurs whenever information is exchanged between an object in the system and an outside agent such as user, a sensor, or another task. The information values exchanged are parameters of events. For example, the event password entered has the password value as a parameter. Events with no parameters are meaningful and even common. The information in such event is the fact that it has occurred a pure single signal. Any time information is input to the system or output from an event to occurs. So for each event, identify actors such as a system, user, or any other external agent that caused the event and parameters of the event. The screen layout or output format generally does not affect the logic of the interaction or the values exchanged. So this is first part of preparing scenario. Then second part, interface formats. Most interactions can be separated into two parts, application logic and user interface. Analysis should concentrate first on the information flow and control rather than the presentation format. The same program logic can accept input from command lines, files, mouse buttons, touch panels, physical push buttons, or remote links. These are the examples for the input for the interface formats. If the surface is detailed or carefully isolated, the dynamic model captures the control logic of the application. So it is hard to evaluate a user interface without actually testing it. Often the interface can be mocked up so that users can try it. Application logic can often be simulated with dummy procedures. Deep decoupling application logic from the user interface allow the look and feel of the user interface to be evaluated while the application is under development. So this is the structure of ATM interface. So you should know, or this is a general structure. So figure shows the possible ATM layout. Its exact details are not important at this point, even less wording of the message. The important thing is the information exchanged in whatever form. Then, third, identifying events. Examine the scenarios to identify all external events. Events include all signals, inputs, decisions, interrupts, transitions, and actions to or from users or external devices. External computation steps are not events, except for decision points that interact with the external world. Use scenarios to find normal events, but does not forget error conditions and unusual events. So group together under a single name events that have same effect of flow of control, even other the parameter values differ. For example, enter password should be an event class since the password values does not affect the flow of control. Similarly, dispense cash is also event of the class since the amount of cash dispensed does not affect the flow of control. Events that affect the flow of control should be distinguished. Account OK, bad account, and bad password are the different events. Don't group them under card status. So you must decide when differences in quantitative values are important enough to distinguish. For example, different digits from a keyboard would usually be considered same event since the high level control does not depend on numerical values. Pushing the enter key, however, would probably be considered a different event since the application would respond differently. The distinction depends or difference depends on the application. You may have to construct a state diagram before you classify all events. Some distinctions between events may have no effect on the behavior and can be ignored. So allocate each type of event to the object classes that send it and receive it. Event is an output event for the sender and input event for the receiver. Sometimes object sends the event to itself, in which case the event both input and output is same for the same class. Show each scenario as event trace and order a list of events between different objects assigned to the column in a table. So this is a state transition diagram. This is the communication between user and ATM. So whenever user inserts card, this is the scenario first. Insert the card to the ATM, then ATM request give the acknowledgement as request password. Give the message. Then user enter the password. Whenever the user enters the password, then ATM send the same password to the consortium to verify that account. Then consortium send to the same message to verify to the bank to verify the card with the bank. If bank account is okay, then bank response bank account is okay to the consortium. Then consortium sends to the account is okay to the ATM. Then ATM sends the message a request of the communication, a request of type, whatever. Then user enters that type. Request ATM communicates request for the amount. User enter expected amount to the ATM. Then ATM process this transaction with consortium. Consortium pass the same transaction toward the bank machine. The process for the transaction, if sufficient balance is in the account, then transaction is successful, otherwise transaction is unsuccessful. Whatever the message said, bank from bank to the consortium, and then consortium to bank. If transaction for the transaction, if there is sufficient balance, then dispenses the cash, then take the cash, then request for continuation. Machine ask request for continuation or not. If user want to continue, then continue, otherwise terminate. This is the communication or state transition diagram between user and ATM. Mm, So these are the two interfaces. First user and second is ATM. But behind this ATM there are two again events, that is consortium and bank computer. These two are invisible. Then this figure shows the event trace for the ATM scenario. If more than one object of same class participates, this is the scenario. The assign the separate column to each object by scanning a particular column in the trace. You can see the events that directly affect to the particular object. Only these events can appear in the state diagram for the object. So the same state diagram, that is data flow diagram or event flow diagram, in the same diagram user ATM consortium bank, there is a no sequence, no message which particular first message come, which second, there is no particular sequence. So this is the event flow diagram, same as state transition diagram. So this figure shows the event between a group of classes such as module. An event flow diagram. The diagram summarizes events between classes without regard for the sequence. Include events for all scenarios, including error events. The event flow diagram is a dynamic counterpart to an object diagram. Paths in object diagram shows the information flows. Paths in the event flow diagram shows possible overflow control flows. Then fourth is building a state diagram. Prepare a state diagram for each object class with non-trivial dynamic behavior, showing the event the object receives and sends. Every scenario or event trace corresponds to a path through the state diagram. Each branch in control flow is represented by a state with more than one exit transition. So start with the event state diagram that affect the class being modeled. Pick a trace showing a typical interaction and only consider the events affecting a single object. Arrange the events into paths whose arcs are labeled by the input and output events found along one column in the trace. The interval between any two events is a state. Give each state a name. If a name is meaningful but does not bother if it is not, the initial diagram will be a sequence of events and state. If the scenario can be repeated indefinitely, close the path in the state diagram. Now find loops within the diagram. If the sequence of events can be repeated indefinitely, then they form a loop. Replace the finite sequence of events with the loops when possible. If in a loop, the first state and the last state are identical. If the object remembers that it has traversed a loop, then two states are not really identical and a simple loop is incorrect. At least one state in a loop must have multiple transitions leaving it, or the loop will never terminate. Now merge other scenarios with the state diagram. Find the point where the state diagram intersect with the scenario and avoid diverse Hello, may I audible? Hello. So building a state diagram, merge other scenarios into a state diagram. Find the point in each scenario where it diverges from the previous scenario. The point corresponds to an existing state in the diagram. Attach the new event sequence to the existing state as an alternative path. While examining states and scenarios, you may think of other possible events that can occur at each state. Add them to the state diagram as well. So this is a possible state diagram for ATM. So there are different classes. These classes is shown rounded, that is elliptical, rectangles.
हॅलो
Hello.
सर.
Huh.
सर स्क्रीन दिसत नाही.
Screen is not visible.
येस.
1 minute. Hello. Hello.
हा सर.
Screen दिसते visible आहे.
हा आहे. दिसते आता.
Okay. This is a possible state diagram for ATM structure. There are different classes. So these classes in state diagram can be shown rounded rectangles which look like sometimes elliptical. See the figure carefully. This is a state diagram for class consortium. So each class has one input and one or more output. This is the input or start. This solid circle indicates the start. This cir solid circle with this figure indicates the outputs. So any machine or any class have one input and one or more outputs. This is a state diagram for consortium class. So here input is process transaction. So in that class process bank a transaction. There are two possibilities. If the balance is sufficient, then bank transaction is succeed, or if the balance is insufficient, then bank transaction failed. There are two outputs. Similarly, to verify the accounts, so this is the input to this class. So verify the bank code. If there is no correct bank account, then output will be the bank bad bank code or bad code. If the account is accurate, then good code sent to the new class. Verify the card with bank. If the card does not contain with that bank, then bad account or bad bank account. This is the output, or bad bank password. There are two outputs in case of bad account or bad password. If it is okay, then bank account will okay and go to the next transaction. These are the class diagrams for the consortium class. Then this is a state diagram for class bank. So process the bank transaction. So update the account. There may be a two outputs, that is transaction failed or success the transaction. Similarly, this is a verify the card with bank. Verify card number. If it is not with the bank, then bad bank account, or if it is with the bank, then valid. Then verify the password. If password is wrong, then bad bank password. If it is password is correct, then valid, or bank account is okay. These are the outputs. So the hardest thing is deciding at which state an alternate path rejoins the existing diagram. Two paths join at a state of the object forgets which one was taken. In many cases, it is obvious from your knowledge of the application that two states are identical. For example, interesting inserting interesting two nickels into vending machine is equivalent to inserting one time. So beware of two paths that appear identical but which can be dis- distinguished or differentiated under some circumstances. For example, some systems repeat the input sequence if the user makes an error entering information but give up after certain number of failures. The differences can be glossed over by adding a parameter such as number of failures to the to remember the information. So these are the building parameters, and the last point from the dynamic modeling is matching events between objects. So check the completeness and consistency at the system level when the state diagrams for each class are complete. Every event should have sender or a receiver. Occasionally, the same object states without the procedures or predecessors or successors are suspicious. Make sure they match the scenario. Objects are inherently concurrent. Beware of synchronization errors where an object occurs at awkward time. The set of state transition diagram for object classes important dynamic behavior constitute the dynamic model for an application. So last second last part from this chapter is functional modeling. The functional modeling shows how values are computed without regard for sequencing, decisions, or object structure. The fundamental model shows which values depend on which other values and the functions that relate them. Data flow diagrams are useful for showing functional dependencies. Functions are expressed in various ways, including natural languages, mathematical equations, and pseudocode. So the process on a data flow diagram correspond to activities or actions in the state diagrams of the classes. The flow of and data flow diagram correspond to the objects or attributes in an object diagram. It is best to construct the functional model after the object and dynamic model. So there are 5 steps for constructing functional model. First, identify inputs and output values. Build a data flow diagram showing functional dependencies. Describe functions. Identify constraints and specify optimization criteria. So first, identify input and output. This figure shows this is there is input and output. So by listing input and output values are the parameters of events between the system and outside the world. So whenever insert a card in ATM, so it this is the input. Then ATM asks for password. This is the output. Whenever user enters the password, this is the input. Then ATM shows the screen. This is the output. So examine the problem statement to find any input or output values that you missed. Then building data flow diagrams. So data flow diagrams showing how each output value is computed from input value. A data flow diagram usually constructed in layers. The loop layer may consist of a single process or perhaps one process each to gather inputs, compute values, and generate outputs. So this is a data flow diagram. So here user inserts card. So ATM machine reads the card, perform for performing transaction. So ATM machine reads the card, then cash card uh, reads in the case of bank code, card code, then perform transaction. So communicate with bank accounts. If there is sufficient balance or insufficient balance, sends the message and that generates the output and the output displayed to the users. This is the data flow diagram regarding the ATM and user communication. Within each data flow diagram layer, the work backward from each output value to determine the function that computes it. If the input to the operation are all inputs of the entire diagram, you are done. Otherwise, some of the operation inputs are intermediate values that must be traced in backward direction. So this is consortium. Whenever user uh, enters card to the ATM, so bank code, that is select bank, then go to the bank, select the card, that is card code. If it is not okay, then bank code is bad. If card is invalid, then invalid card code. So if it is card is valid, then go to the forward direction card authorization, or sometimes go to the account. So verify the password and select account. If all are okay, then go to the account, then update the balance, update the account, then whatever transaction may be done, then there is receipt. If transaction is failed, then bad transaction. This is the building data flow diagrams. So in each state it depends on the functions. Sometimes if the input of operation all inputs the entire diagram, otherwise some operations input intermediate values that must be traced in backward direction. So most of system contains internal storage objects that retain values between interaction. The ATM communication reads and writes values from the account object. An internal store can be distinguished from the data flow or process because it receives the value that do not result in immediate outputs but instead are used at some distant time in the future. DFD specifies only dependencies among the operations. They do not show decisions or sequencing of operations. In fact, some operations can be optional or mutually exclusive. So third is describing functions. When a DFD has refined enough, write a description of each function. The description can be in natural language, mathematical equation, pseudocode, decision tables, or some other appropriate forms. So focus on what the function does, not how to implement it. The description can be declarative or procedural. A declarative description specifies the relationship between input and output values and the relationship among the output values. A procedural description specifies a function by giving an algorithm to compute it. The purpose of the algorithm is only to specify what the function does during implementation. Any other algorithm that computes the same values can be substituted. So fourth one is identifying constraints between objects. So identify constraints between objects. Constraints are the fundamental dependencies between objects that are not related by input-output dependency. Constraints constraints can be on two objects at same time between instances of the same object at different times. or between instances of different objects at different times. So preconditions on functions are constraints that the input values must satisfy, and post conditions are constraints that the output values are guaranteed to hold. State the times or conditions under which the constraints hold. And last point from functional modeling is specifying optimization, in that specify values to be maximized, minimized, or otherwise optimized. If there are several optimization criteria that conflict, indicate how to trade off to be decided. Optimization criteria for the ATM example must include: minimize the number of physical messages sent between different sites, minimize the time an account is locked for concurrency reasons. It is extremely urgent to minimize the time an entire bank is locked for concurrency reason if such locking is needed. Next point is adding operations. So our style of object oriented analysis places much less emphasis on defining operations than more traditional programming based object oriented methodologies. The list of potential the list of potentially useful operations is open ended, and it is difficult to know when to stop adding them. Operations in object-oriented programming languages can correspond to queries about attributes or associations in the object model, such as account.balance or cashcard.bank, to events in the dynamic models, such as cancel set from user to ATM, and the functions in functional models such as update the account. So there are six key operations should be now summarized in object model. So there are discovered during the following 6 points. So first is operation from object model. Second, operations from events. Third, operation from state actions and activities. Fourth, operations from functions. Fifth, shopping list operations. And sixth, simplifying operations. So operations from object model. Operations from object structure include reading and writing attribute values and association links. These operations need not be shown explicitly on the object model, but they are implemented in the presence by the presence of an attribute. During analysis, it is assumed that all attributes are accessible. A dot notation is convenient to indicate that the attributes such as ATM, cash on hand. Second is operations from events. Each event sent to object corresponds to an operation to the object. Depending on the system architecture, events can be implemented directly by including an event handler as a part of system substrate, or they can be converted into explicit methods. During analysis, events are best represented as labels on state transitions and should not be explicitly listed in the object model. Then third part, operations from the state actions and activities. Actions and activities in state diagrams may be functions. These functions having interesting computational structure should be defined as operations on the object model. For example, in ATM consortium has the activity verify bank code and bank has activity verify the password. Fourth one, operations from the function. Each function in DFD corresponds to an operation on an object. These functions frequently have interesting computational structures should be summarized on the object model. Organize the functions into the operations on the object. Omit access functions that traverse to the object model. If the same series of equations or pseudocode fragments describe more than one function, then new operation can be introduced to simplify the functional model. Then fifth one, shopping list operations. Sometimes the real world behavior of classes suggests the operations, and this calls a shopping list because the operations are not depend on the particular application nor subject to particular order of execution but meaningful in their own right. Okay, then shopping list operations permit considering future possible needs while the organization of classes is still fluid. They provide an opportunity to broaden or big the base of an object definition beyond the narrow needs of the immediate problem. They are meaningless for a purely functions oriented problem decomposition but make sense because the objects have a real world meaning that transcends their use in single problem. Then simplifying operations. Examine the object model to similar operations and variations in on a single operation. Try to mm, broader broaden a definition of an operation to encompass such variations and special cases. Use inheritance where possible to reduce the number of different operations. Introduce new subclasses as needed to simplify the operations, provided that the new subclasses are not forced and unnatural. Locate each operation at the correct level within the class hierarchy. The result of this refinement is often favor more powerful operations that are nevertheless simpler to specify than the original operations because they are more uniform and general. The ATM example is not complex enough to require simplification. So last point from this chapter is iterating the analysis. Most analysis models require more than one pass to complete. Most problem statement contains circularities and most application cannot be approached in a completely linear way because different parts of different interact because different parts of the problem interact. To understand a problem with all its implications, you must attack the analysis interactively, preparing the first approximation to the model and then interacting iterating the analysis as your understanding increases. There is no firm line between analysis and design, so do not overdo it. Verify the final analysis with the requester and the application domain experts. So there are 3 points: refining the analysis model, restating the requirements, analysis and design we will see in detail. So first one, refining the analysis model. The overall analysis model may show inconsistencies and imbalances within and across models. Iterate the different stages to produce cleaner, more coherent design. Attempts to refine objects definitions to increase sharing and improve structure. Add details that you glossed over during the first pass. The common omission of physical object that has two logically distinct aspects. They should be modeled with a distinct object for each aspect. An indication of this is an object that does not fit in cleanly because of its need to fill in two roles. So other indications to watch for include exceptions, many special cases, lack of expected symmetry, and an object with two or more sets of unrelated attributes or operations. Consider restructuring your model to better capture constraints within the structure. Remove objects or association that seemed useful that first but now appear extraneous. Often two distinct objects in the analysis can be combined because the distinction between them does not affect the rest of the model in any meaningful way. A good model feels right and does not appear to have extraneous detail. Even a good model will often have a few small areas where a design is adequate but never feels quite right. Second point is restating the requirement. When the analysis is complete, the model serves as the basis for the requirements and defines the scope of the future discourse. Most of the real requirements will be the part of model. Some requirements specify performance constraints. These should be stated clearly together with the optimization criteria. Other requirements specify the method of the solution. These should be separated and challenged if possible. So final models should be verified with the requester during analysis. Some requirements may appear to be incorrect or impractical. Corrections to be the requirement should be confirmed. The analysis model should also be verified by application domain expert to make sure that it co- correct, correctly models the real world Final verified analysis serves as the basis for the system architecture, design and implementation. The original problem statement should be revised to incorporate corrections and understanding discovered during analysis. And last part from this point, analysis and design. The goal of the analysis is to fully specify the problem and application domain without introducing a bias to any particular implementation, but it is impossible in practice to avoid all taint of implementations. There is no absolute line between the various design phases, nor is there any such thing as perfect analysis. The purpose of the rules is to preserve flexibility and permit changes later. But remember that the goals of modeling is to accomplish the total job, and flexibility is just a means to an end. So, whatever we have studied during this chapter, let us summarize. So, purpose of analysis is to state and understand the problem and the application domain so that the correct design can be constructed. A good analysis captures the essential features of problem without introducing implementation artifacts that prematurely restrict the design decisions. First, write an initial problem statement in consultation with requester, users, and domain experts. The requirements should describe what needs to be done, not how it will be implemented. The problem statement may be incomplete, ambiguous, or erroneous. It is just a starting point. So object model shows the static structure of the real world. First, identity object classes, then identify association between objects, including aggregation. Object attributes and links should be identified, although minor one can be deferred. Inheritance should be used to organize and simplify the class structure. Organize tightly coupled classes and association into module. Information in object modules should be supplemented with brief textual description, including the purpose and scope of each activity or entity. Then dynamic model shows the behavior of the system, especially sequencing of interactions. First, prepare scenarios of typical and exceptional sensations. Then identify external events between the system and outside the world. Build state diagrams for each active object showing the patterns of the events it receives and sends together with the actions that it performs. Match events between state diagrams to verify consistency. The resulting set of state diagrams constitute the dynamic model. Then functional model shows the functional derivations of values without regard for when they are completed. First, identify input and output values of the system as a parameters of external events. Then construct data flow diagrams to show the computation of each output value from other values and ultimately the input values. Data flow diagrams interact with internal objects that serves as data stores between interactions. Finally, specify constraints and optimization criteria. Then we have studied operations. Operations are derived from several sources in this methodology, and we do not find it useful to group them together during analysis. Only the operations from the functional model and the possibly shopping list operations need be shown on the object diagram. Methodologies are never as linear as they appear in the books. This is this one is no exception. Any complex analysis is constructed by iteration on multiple levels. All parts of the model need not be developed at the same pace or same structure. The result of the analysis replaces the original problem statement and serves as the basis for design. So this is the end of the chapter.